Exomoons in our backyard? What Saturn and Jupiter's moons teach us about alien worlds. Part 1. The hunt for moons beyond our solar system. The universe is vast, and with it comes an almost unfathomable number of celestial bodies. For decades, astronomers have focused on exoplanets, worlds orbiting stars beyond our sun. But what about exomoons, natural satellites orbiting these distant planets? The search for exomoons is a relatively new frontier, fraught with observational challenges due to their small size and close proximity to their parent planets. However, the potential discovery of a truly Earth-like exomoon, possibly harboring life, fuels this ambitious quest. This ongoing hunt leverages sophisticated telescopic techniques, including transit photometry, where a dip in starlight indicates a planet, and perhaps a moon passing in front of it. The challenges in detecting exomoons are significant. A moon's tiny gravitational tug on its exoplanet is extremely difficult to measure from light years away. Furthermore, the light emitted or reflected by an exomoon is often dwarfed by the glare of its host star and even its parent exoplanet. Researchers are developing new algorithms and computational models to sift through vast datasets, searching for the subtle signatures that might betray an exomoon's presence. Every flicker and fluctuation in starlight holds potential clues, and the refinement of these detection methods is a critical step towards confirming the first definitive exomoon. Despite these hurdles, theoretical predictions suggest that exomoons should be abundant throughout the cosmos. Many exoplanetary systems discovered so far feature gas giants, much like Jupiter and Saturn in our own solar system, which are known to host numerous moons. It is reasonable to extrapolate that similar systems elsewhere would also possess a retinue of satellites. The quest for exomoons, therefore, is not just about finding individual objects, but about understanding a potentially widespread phenomenon that could significantly expand the inventory of potentially habitable worlds in the galaxy. One promising technique involves observing transit timing variations and transit duration variations. If an exoplanet has a moon, its transit across its star might be slightly delayed or arrive early, or the duration of its transit might vary due to the gravitational interaction between the planet and its moon. These subtle deviations are exceedingly small, but with precise enough instruments, could provide compelling evidence. The next generation of space telescopes, with their enhanced sensitivity and observational capabilities, are expected to play a crucial role in pushing this frontier forward, perhaps even revealing the atmospheric composition of some of these distant worlds. The motivation behind the exomoon hunt is profound. If life can arise on moons, then the total number of potentially habitable environments in the universe could dramatically increase. Moons offer a different set of conditions compared to planets, some of which might even be more conducive to life. For instance, tidal heating from a giant planet could maintain subsurface oceans on a moon, providing a stable environment for billions of years, even if the moon itself is far from its star. This broadens the scope of where we might expect to find extraterrestrial biology, making the search for exomoons a central theme in astrobiology. Part 2. Europa's ocean as a model for habitability. Jupiter's moon Europa is a prime candidate in our solar system for harboring extraterrestrial life, primarily due to compelling evidence of a vast saltwater ocean hidden beneath its icy shell. This subsurface ocean is believed to be in direct contact with a rocky seafloor, a critical ingredient for life as we know it, allowing for hydrothermal vents and chemical reactions that could provide energy and nutrients. The continuous interaction between water and rock, fueled by tidal heating from Jupiter's immense gravity, creates a dynamic environment, analogous to the deep-sea ecosystems found on Earth. The thickness of Europa's ice shell is still debated, but estimates range from a few kilometers to tens of kilometers. This icy barrier provides protection from harmful radiation from Jupiter, creating a stable environment for the ocean below. While sunlight does not penetrate this far, chemosynthesis, a process where organisms derive energy from chemical reactions, could thrive. The study of Europa's unique geology, including chaotic terrains and linear features on its surface, offers clues about the dynamics within its interior and the processes that might be exchanging material between the ocean and the surface. Future missions, such as Europa Clipper and the Europa Lander concept, aim to investigate this tantalizing ocean in unprecedented detail. Europa Clipper will conduct numerous close flybys, using radar to probe the ice shell and spectrometers to analyze potential plumes emanating from the Moon, which could offer direct samples of the subsurface ocean. Such missions represent humanity's most ambitious attempt to determine if life has indeed emerged on another body within our solar system. The data gathered will be invaluable for understanding not only Europa, but also the potential for similar conditions on distant exomoons. The concept of a habitable subsurface ocean on an icy moon challenges traditional notions of the habitable zone, which typically refers to a region around a star where liquid water can exist on a planet's surface. Europa demonstrates that habitability can extend far beyond this stellar habitable zone, powered instead by internal geological processes. This expands the potential real estate for life dramatically, suggesting that many icy worlds orbiting gas giants, even those at great distances from their stars, could possess the necessary conditions for supporting microbial ecosystems. The implications for exomoon research are immense. If Europa's ocean is confirmed to be habitable, it provides a powerful analog for what we might expect to find around other giant planets. Astronomers searching for exomoons can then prioritize targets that share similar characteristics: icy surfaces, proximity to large planets that could induce tidal heating, and evidence of geological activity. Europa serves as a tangible, nearby example of a potentially living world, offering a blueprint for the search for life beyond Earth, extending the reach of astrobiological investigations deep into interstellar space. Part 3. Ganymede's Magnetic Field and Hidden Sea. Ganymede, the largest moon in our solar system, presents another compelling case for subsurface oceans, but with an additional intriguing feature: it possesses its own intrinsic magnetic field. This makes Ganymede unique among all solar system moons. This magnetic field is generated by a convection of liquid iron within its core, much like Earth's geodynamo. The presence of such a field indicates a hot, active interior and offers further evidence of a dynamic moon, far from being a geologically inert body. This magnetic protection could have profound implications for any life that might exist within its hidden ocean. The magnetic field of Ganymede carves out its own mini-magnetosphere within Jupiter's enormous magnetic field, a fascinating interaction that provides insights into the internal structure of the moon. This magnetic cocoon offers a degree of shielding from Jupiter's intense radiation belts, which are otherwise highly energetic and potentially damaging to organic molecules. For any potential subsurface life, this natural protection would reduce the destructive effects of high-energy particles, potentially allowing for more stable conditions over billions of years. Evidence for Ganymede's ocean comes from observations by the Galileo spacecraft, which detected shifts in the moon's magnetic field that are best explained by the presence of a salty, electrically conductive liquid layer beneath its ice. This ocean is thought to be sandwiched between multiple layers of ice, possibly including a high-pressure ice layer at the bottom, separating it from the rocky core. The thickness of Ganymede's ocean is estimated to be enormous, perhaps even exceeding the combined volume of all of Earth's oceans, making it a truly colossal reservoir of liquid water. The existence of a powerful magnetic field and a vast subsurface ocean makes Ganymede a key target for future exploration. The European Space Agency's JUICE mission, set to arrive at Jupiter in the early 2030s, will focus extensively on Ganymede, performing multiple flybys and eventually entering orbit around the Moon. Its instruments will precisely map the magnetic field, probe the ice shell with radar, and study the Moon's overall composition and structure. These investigations will provide critical data to confirm the ocean's properties and assess its potential for habitability. From the perspective of exomoon research, Ganymede provides an example of a moon with multiple potential factors supporting habitability. Not only does it have a massive ocean, but its magnetic field offers an additional layer of environmental stability and protection. This suggests that astronomers searching for exomoons around distant gas giants might consider systems where the exoplanets themselves could induce strong tidal forces, potentially leading to similar internal heating and the formation of both subsurface oceans and intrinsic magnetic fields on their moons. Part 4. Enceladus and its icy geysers. Saturn's moon Enceladus is one of the most exciting candidates for life in our solar system, largely thanks to the dramatic plumes of water vapor and ice particles erupting from its south polar region. These geysers, discovered by the Cassini spacecraft, are direct evidence of a subsurface ocean beneath a relatively thin ice shell, a global ocean now known to be in contact with a rocky core. The composition of these plumes, which contain salts, silicates, and organic molecules, strongly suggests the presence of hydrothermal activity at the seafloor, providing a chemical energy source crucial for life. The continuous eruption of these plumes offers an unprecedented opportunity to sample an extraterrestrial ocean without ever landing on the Moon or drilling through its ice. Cassini's multiple flybys through the plumes allowed it to directly analyze their contents, revealing a rich cocktail of ingredients that closely resemble the conditions found around hydrothermal vents on Earth, which support vibrant ecosystems in complete darkness. This discovery has transformed our understanding of where life might exist, moving from surface-based water to deep hidden oceans. The energy driving Enceladus's activity comes from tidal heating, generated by Saturn's immense gravitational pull. As Enceladus orbits, the flexing of its interior creates friction, melting ice and sustaining the ocean. This continuous energy input, along with the interaction between water and rock, provides a dynamic environment conducive to prebiotic chemistry and potentially the emergence and sustenance of life. The thinness of the ice shell in the south polar region further facilitates the eruption of the plumes, creating the direct link to the ocean. Future missions to Enceladus are being discussed, aiming to further investigate the ocean and its potential for life. Concepts include spacecraft that would fly through the plumes with more advanced instruments, and even landers designed to taste the plumes directly or explore the surface for frozen ocean material. Such missions would seek definitive biomarkers, evidence of biological processes, which would confirm whether Enceladus truly harbors living organisms. The accessibility of its ocean through the plumes makes it a scientifically attractive target for astrobiological exploration. Enceladus serves as a critical analog for potentially habitable exomoons. Its demonstrated plumes mean that, in theory, if a similar exomoon existed, its chemical composition could potentially be studied from light years away using advanced telescopes, assuming the plumes are substantial enough. The existence of an active, hydrothermally sustained ocean beneath a relatively thin ice shell, driven by tidal forces, provides a clear model for what astronomers might look for when assessing the habitability of moons orbiting gas giants beyond our solar system. Part 5. Titan's methane seas and thick atmosphere. Titan, Saturn's largest moon, presents a radically different but equally fascinating model for an alien world, offering insights into the diversity of potentially habitable environments. Unlike Europa or Enceladus, Titan possesses a thick, hazy, nitrogen-rich atmosphere, even denser than Earth's, and a unique hydrological cycle based on liquid methane and ethane instead of water. Its surface is sculpted by rivers, lakes, and seas of hydrocarbons, making it the only other body in the solar system known to have stable liquid on its surface. The Huygens probe, part of the Cassini-Huygens mission, successfully landed on Titan's surface in 2005, providing humanity with its first direct view of a landscape dominated by these exotic liquids. The images revealed a diverse terrain, including shorelines, drainage channels, and even what appeared to be methane rain. This rich chemical environment, with complex organic molecules forming in the atmosphere and raining down onto the surface, offers a natural laboratory for studying prebiotic chemistry in conditions vastly different from Earth's. While the temperatures on Titan are extremely cold, far below the freezing point of water, the presence of liquid on its surface and a thick atmosphere suggests that complex chemical processes could still be active. Scientists ponder the possibility of a different form of life, perhaps based on methane as a solvent rather than water, or employing different biochemical pathways. This pushes the boundaries of our understanding of life and demonstrates that habitability might extend beyond our familiar water-based paradigm. Beneath Titan's icy crust and potentially deep within its interior, evidence also suggests the presence of a subsurface liquid water ocean, separate from its surface hydrocarbon lakes. This water ocean, likely mixed with ammonia, would be sustained by internal heating and could offer another, more Earth-like environment for potential life. The complex interplay between the surface chemistry, the thick atmosphere, and a possible subsurface water ocean makes Titan a multi-layered enigma for astrobiological research. Titan's thick atmosphere and exotic surface liquids provide a crucial analog for exomoons that might be found in similar cold outer regions of distant star systems. The moon teaches us that life, or at least complex chemistry, doesn't necessarily require liquid water on the surface and can adapt to extreme conditions, utilizing alternative solvents and energy sources. When astronomers detect exomoons with thick atmospheres, Titan reminds us to consider a broader range of chemical compositions and potential habitability, even those seemingly inhospitable by Earth-centric standards. Part 6. Lessons from Io's volcanic world. Jupiter's innermost large moon, Io, stands in stark contrast to the icy worlds of Europa and Enceladus. It is the most volcanically active body in our solar system, a true hellscape of sulfurous plains and towering volcanic plumes that continuously reshape its surface. This extreme geological activity is driven by immense tidal forces exerted by Jupiter and the other Galilean moons. The constant gravitational tug-of-war generates internal friction, heating Io's interior to such an extent that its mantle is largely molten, leading to spectacular and relentless eruptions. Io's surface is completely devoid of water, and its volcanic nature makes it an unlikely candidate for life as we know it. However, Io offers invaluable lessons for understanding planetary and lunar evolution, particularly the powerful role of tidal heating. The sheer scale of its volcanism provides a dramatic demonstration of how gravitational interactions can profoundly influence a celestial body's internal dynamics, even overriding the effects of stellar radiation or inherent internal heat from formation. The study of Io helps us comprehend the limits of tidal heating and its potential impacts on moons around exoplanets. While Europa and Enceladus show how tidal forces can create life-sustaining subsurface oceans, Io reveals the extreme end of this spectrum, where tidal heating can be so intense that it sterilizes a world, creating a surface utterly hostile to life. This understanding is crucial for assessing the habitability of exomoons, as it allows astronomers to identify scenarios where tidal forces might be too destructive rather than beneficial. Observations of Io, primarily from spacecraft like Voyager, Galileo, and New Horizons, have revealed its dynamic surface, with lava flows reaching hundreds of kilometers and plumes erupting hundreds of kilometers into space. Its rapidly changing surface features make it a truly living world, albeit one where life would struggle to exist. The energy output from Io's volcanism is truly staggering, dwarfing the total geothermal energy released by Earth. For the search for exomoons, Io serves as a cautionary tale and a parameter guide. When considering exomoons orbiting large gas giants in close proximity, astronomers must factor in the potential for extreme tidal heating that could render a moon too hot or too geologically active to sustain life. Io helps define the upper boundary of tidal heating effects, guiding researchers to look for exomoons in orbital configurations, where tidal forces are strong enough to create oceans, but not so intense as to create an uninhabitable volcanic inferno. Part 7. Moons as possible cradles of life. The revelations from moons within our own solar system have dramatically expanded the range of environments considered potentially habitable, moving beyond the traditional focus on planets. Moons like Europa and Enceladus, with their subsurface oceans, demonstrate that liquid water, a fundamental requirement for life, can be sustained for billions of years through internal heating, even in the cold outer reaches of a star system. This shifts the paradigm, suggesting that moons could be far more prevalent cradles of life than previously imagined. The unique conditions on moons, such as tidal heating, offer distinct advantages for the emergence and evolution of life. The constant flexing and internal friction can drive hydrothermal activity, providing the chemical energy and nutrient cycling necessary for organisms. Furthermore, a thick ice shell, as seen on Europa, provides excellent protection from harmful cosmic radiation, creating a stable, shielded environment that could allow life to flourish without the need for a strong magnetic field of its own or a dense atmosphere. The study of our solar system's moons also highlights the diversity of potential life-sustaining mechanisms. Titan, with its methane lakes and thick atmosphere, pushes the boundaries of what constitutes a habitable environment, suggesting that life might not always require water as a solvent. This broadens the astrobiological scope, encouraging scientists to consider alternative biochemistries and energy sources, vastly increasing the number of potential locations where life could arise across the universe. The prevalence of gas giants in discovered exoplanetary systems further strengthens the argument for exomoons as potential cradles of life. Many of these exoplanets are in orbits that would make their moons highly susceptible to tidal heating, potentially fostering conditions similar to Europa or Enceladus. The sheer number of potential exomoon hosts suggests that the total count of habitable worlds in the galaxy could be significantly higher than if we only considered planets in the stellar habitable zone. Ultimately, moons offer a unique niche for life, different from their parent planets. Their diverse geological and atmospheric properties, driven by complex gravitational interactions and internal heating, create a rich tapestry of environments where life could potentially thrive. The ongoing exploration of our own solar system's moons is not just about understanding our backyard, but about developing a comprehensive framework for searching for life on countless exomoons that undoubtedly exist beyond our stellar neighborhood. Part 8. How studying moons helps find exoplanets. While the primary goal of studying our solar system's moons might seem to be understanding habitability and the potential for life, this research also provides invaluable insights that indirectly aid in the broader search for exoplanets and exomoon systems. The detailed geological, atmospheric, and orbital dynamics observed in our own system serve as templates for interpreting the often subtle data gathered from distant star systems. Understanding how moons interact with their parent planets and stars helps refine models used to detect and characterize exoplanetary bodies. For instance, the precise measurements of lunar orbital perturbations and gravitational interactions within our solar system inform the development of sophisticated algorithms used to detect exomoons. By understanding how Jupiter's gravity affects its Galilean moons, or how Saturn's influence shapes Enceladus's plumes, scientists can better predict and interpret the transit timing variations and transit duration variations that might betray the presence of an exomoon around a distant exoplanet. This detailed local knowledge is directly transferable to the exoplanet hunting field. Furthermore, studying the diverse compositions and atmospheres of our moons provides a foundational understanding for interpreting spectroscopic data from exoplanets. If an exoplanet is found to have a moon with a thick atmosphere like Titan, or an icy surface indicating a subsurface ocean like Europa, these insights help to contextualize and characterize the exoplanet itself. The moon's presence and characteristics can often tell us more about the broader environment of the exoplanetary system. The various geological processes observed on our moons, such as volcanism on Io or cryovolcanism on Enceladus, also help scientists understand the internal dynamics and energy budgets of rocky and icy worlds. This knowledge is crucial for estimating the mass, density, and internal heat of distant exoplanets, even those where only atmospheric or transit data is available. Our moons provide concrete examples of how internal heating, driven by various mechanisms, can manifest on the surface and in the atmosphere. In essence, our solar system's moons are laboratories in miniature, offering a diverse array of planetary science phenomena that are directly relevant to exoplanet research. By meticulously studying these nearby celestial bodies, we build a comprehensive knowledge base that allows us to ask better questions, design more effective observational strategies, and ultimately make more accurate interpretations of the limited data we can gather from truly alien worlds. This synergy accelerates our progress in mapping the universe's exoplanetary landscape. Part 9. Science fiction dreams of living on moons. For decades, science fiction has explored the captivating idea of humanity colonizing moons, envisioning them as diverse and often challenging homes beyond Earth. From the iconic images of domed cities on the moon to sprawling underground complexes on Jupiter's satellites, these narratives reflect our innate desire to explore and expand, pushing the boundaries of what is possible. Europa, Ganymede, and Titan, with their distinct environments, have frequently served as backdrops for tales of human ingenuity and resilience in the face of alien landscapes. The concept of living beneath the ice on Europa, tapping into its vast subsurface ocean, has been a particularly potent idea in fiction. Stories imagine submarines navigating its hidden depths, or scientific outposts established at hydrothermal vents, exploring an entirely new biosphere. These narratives often delve into the challenges of extreme pressure, cold, and radiation, but also the allure of discovering unprecedented forms of life and the wonders of a truly alien aquatic world. Titan, with its thick atmosphere and hydrocarbon lakes, has inspired visions of humanity adapting to radically different conditions. Science fiction authors have depicted cities floating in its dense atmosphere, or intrepid explorers navigating its methane seas in specially designed vessels. The challenge of breathing an alien atmosphere and interacting with a cryogenically cold, hydrocarbon-rich environment fuels creative solutions, pushing technological boundaries in the realm of imagination. Ganymede, with its sheer size and potential multi-layered ocean, offers another compelling canvas. Its intrinsic magnetic field, a unique feature among moons, might provide a crucial shield for future human settlements against Jupiter's harsh radiation. Fiction has explored the concept of building vast habitats on its icy plains, perhaps even utilizing its rich water resources for fuel or life support, and establishing humanity's largest off-world colony. These science fiction narratives, while speculative, often draw inspiration from real scientific discoveries and pose important questions about our future in space. They encourage us to think about the practicalities of extreme environment survival, the ethical implications of encountering alien life, and the long-term sustainability of human expansion. In turn, these imaginative visions can sometimes even inspire real scientific and engineering endeavors, blurring the lines between fiction and future reality in our quest to explore the cosmos. Part 10. Could alien moons already exist out there? Given the wealth of moons in our own solar system and the sheer number of exoplanets discovered, it is highly probable that alien moons or exomoons already exist in vast quantities across the universe. The conditions for moon formation are common, as planets accrete material during their formation or capture smaller bodies, and giant planets frequently host numerous satellites. The real question is not whether they exist, but rather how many are detectable and how many harbor conditions conducive to life. Astronomers have already found tantalizing hints of exomoons. For instance, observations of exoplanet Kepler 1625b showed unusual transit signatures that could potentially be explained by the presence of a Neptune-sized exomoon. While not definitively confirmed, such observations fuel the optimism that robust detections are on the horizon. The ongoing refinement of observational techniques and the deployment of more powerful telescopes are bringing us closer to confirming the first definitive exomoon. The implications of discovering ubiquitous exomoons are profound for the field of astrobiology. If moons are common and some can support liquid water and chemical energy, then the total number of potentially habitable worlds in the galaxy could be significantly larger than current estimates based solely on planets. This dramatically increases the statistical probability of life existing beyond Earth, making the search for extraterrestrial intelligence an even more compelling endeavor. The diverse array of environments observed on our own moons, from the subsurface oceans of Europa and Enceladus to the methane lakes of Titan, suggests that habitability can manifest in many different forms. This knowledge prepares us for the possibility that alien moons, when discovered, might surprise us with their unique characteristics and perhaps even harbor forms of life that challenge our current definitions. The universe is likely far more creative in fostering life than we can currently imagine. In conclusion, the study of our solar system's moons is not merely an academic exercise. It is a critical stepping stone in the grand quest to understand our place in the universe. Each moon offers a unique piece of the puzzle, providing analogs for the exomoons we hope to discover. The certainty that alien moons exist, coupled with the growing capability to detect them, means that the next great revolution in astrobiology might very well come from these smaller, often overlooked, but potentially vibrant worlds orbiting distant stars.